Well, we call it the equation that involves separation of variables. I know, we call it separable. It's kind of boring, yeah.
Did you get the e to the RT, like the last step? Wouldn't it be 1 over e to the RT, like when you divide it out?
Oh, it's because 1 over e to the minus RT is e to the RT. If you like, that's, I mean, I could do more steps. E to the minus RT to the minus 1, which is e to the minus RT times minus 1, which is e to the RT. I mean, however you want to look at it, but it is e to the RT. Now this differential equation is important because it comes up, for example, in the charging capacitor problem or like the charging inductor problem. I believe both of these involve a first order differential equation in time of this form. They're both linear. And so in that context, y might be current or it might be charge. But this is exactly the nature of the differential equation. And it's a lot of the reason that this material is in calculus 2 is because engineering departments everywhere want engineers to know about the integrating factor method so that they can solve the charging capacitor problem and the, charging inductor problem logically. Yeah.
So G wasn't meant to be gravity?
No, G is not gravity here. So, yeah, let's put G equal to 1. What happens? What happens if we put G equal to 1? We've got what? Y equals to e to the RT times the integral of e to the minus RT times 1 dt. What solution do we get in that case? E to the RT times what? I think it's minus 1 over r, e to the minus RT, right? Plus a constant, yeah? And so the answer is C, e to the RT. Notice that these cancel and just leave you minus 1 over r. So that's the, this would be the solution in the case that G is equal to 1. I could put 9.8 there if you'd like. It would just put a 9.8 over the, yeah.
So no matter what C is, that solution is going to have the same derivative? How is that possible?
No matter what C is.
So it's a solution to the original differential equation.
Mm-hmm.
And that means no matter what C is, it has the same differential, right?
If you're saying that you're saying it's, I think you're talking about G, not C, aren't you?
I'm talking about your constant. The C. The arbitrary constant.
Right. No matter what C, say what you said again. No matter what C, it's.
So regardless of what C is, let's say, I don't know, in one case it's 1, in another case it's 5. You're going to have the same differential equation?
Yeah. Oh yeah, we can check it, right? At the end of the day, we can judge whether or not we're successful or not by just differentiating it and seeing if it works, right? So what is dy dt here? I mean, we can calculate it, right? So the derivative of this is C r e to the RT by the chain rule, right? And the derivative of that constant, 0. So that's the derivative. And then we're supposed to look at what? Dy dt? To judge whether or not it worked, we have to check is dy dt minus r times y, what's that equal to, right? So dy dt, we just calculated. It's c r e to the RT minus r times y. What was y? Well, y was c e to the RT minus 1 over r. So no matter what c is, they cancel. See, no matter what c it is, the pattern here conspires for these guys to cancel out. And what are you left with? R, and then this 1 over r, right? So that gives you 1, which of course is what I call G in our current context.
Okay.
So it works, yeah. I think perhaps the even other interesting thing here is no matter what you make G, right? All right, hypothetically, no matter what you make whatever we make you, this is called the forcing function here in terms of the application and differential equation. Usually it's called the quote-unquote forcing function, or sometimes it's called the inhomogeneous term. No matter what you inhomogeneous, big words. All right, inhomogeneous term. No matter what that is, no matter what that is, you always pick up the same c e to the RT. See, this term right here is inevitable in sense of that's just coming from adding a constant in the integration of g. So no matter what your choice of g is, that's always there. That's called the homogeneous solution to the differential equation. It's what the differential equation is responding to independent of g. It's like, you could think of it in terms of like a charging capacitor. This is something like the voltage source, which is charging the capacitor. This is just like the resistance in capacitor, how it's responding to the voltage source. So like the homogeneous solution is just due to the resistance in the capacitor, whereas the inhomogeneous term is coming from the voltage that you're putting on it. Something like that is an interpretation. But anyway, so this will happen no matter what we choose for g. All right? So in the notes, I have explored a couple different other choices. This is example 4.3. If you look in there, I've got like what happens when you put g equals to e to the minus RT, and what happens when you put it, as an exponential where the exponential doesn't match the r. It's interesting. Different things happen. So I would encourage you to read example 4.3. If you understand it, it will make differential equations less surprising to you when you get there. Okay, so let's go on to another example. And this is a question. Yeah.
Is this where the Laplace transform comes from?
No. Well, where does the Laplace transform come from? That's, man, I don't have a good answer for that. That's a hard question. There's like this 30-minute video by this MIT professor explaining where it comes from in terms of an analog between discrete signal processing and its continuous extension to integration, which for some reason makes sense to his audience. But I've not, if you read differential equations books, none of them really explain where the Laplace transform. I can explain to you what it does. Just like I haven't explained to you where this came from either today. Did I explain why we're writing I equals this? I have not. I've explained to you how it works, but I didn't derive it from some more basic principle. There is a more basic principle which can be derived from. It's part of a larger story about symmetries of differential equations. The fact that this integrating factor works underlies there's a translational symmetry to this differential equation. There is something to say there, but it's beyond this course. All right. So for us, the integrating factor method is it's just a method we use to solve linear differential equations. It's just that. Yeah.
It's probably a dumb question, but when you took the integral of negative r dt,
Yeah.
how did you just get negative RT? On the left side, top left side of the board.
Oh, this?
Yeah.
Oh, that's just because the integral of, don't think too hard. So like, integral of minus r dt, right? Pull minus r out as the constant, integral dt. So that's minus RT, because remember, yeah, r is a constant. And remember, we're not adding a constant here because we learned that it just multiplies the whole thing by a number. We don't care about that. So, yeah. Mm-hmm.
When you say g is a function of t,
Yeah.
do you mean that g is obviously, it's not constant, then, like, would that be?
Well, one is a particularly silly constant, a function of t. This is the constant function of t.
Yeah.
But yeah.
But could g be like t squared or something like that?
Yeah, g could be t squared, sure.
It still works.
Yeah, if we did that, I could write the solution down. If we put g equals to t squared, I'll write over here. If we put, sorry, people on this floor. If we put g equal to t squared, then we get y equals to c e to the RT plus what? The integral of, oh, why did you do that to me? Monster. Integral of, oh man. See, now I'm gonna actually have to think. So t squared. See, because integration requires thinking. It just always does. There's no getting away from it. How do you integrate t squared e to the minus RT? Integration by parts 2 times. So there we go. All right, I just don't feel like doing it at the moment. Yeah. Yep. Yes, sir.
What section of notes should we be looking at?
We are in the first order, which is my ridiculous title for this section of notes. And we're in section 4. Like I'm on page 12 of the notes. Yeah. All right. Let me see if I can. Are you saying the book is chapter 9? That sounds right. And I think it's section 9.4 we're in, if I remember right, maybe 5. It's the integrating factor method.
Did we skip chapter 8?
Not in my notes. But yes, but we'll come back to it. Listen, so Dr. Sperano, yeah, he's covering arc length and surface area, things like that. We'll come back to arc length at the end of the course because, in my view, those things come alive when we use parametric equations, and so until then, I'd just rather not talk about them. Yeah.
Will we eventually start using this to do basically G substitutions for entire functions of?
Oh, yeah. I don't intend this as a theorem. It's just kind of an example that has. I'm not intending this is something you memorize and apply. No, this is just an example. So in terms of like, test or something, I would likely just have the t squared over there rather than, and maybe I might have r as a number, as a constant like this. I don't know. I might have it as 3, So let me see if I can come up with another example. This one's dangerous though because it's not in my notes. Ruh-roh is right. All right. Oh, let's see what happens if we do dy dx plus, I don't know, 3 over x squared y equals to, I'm going to put a sign of something to be TBD, sign of TBD, to be determined. All right. So, sorry, like Dr. Cook, shouldn't you prepare for class and like have these things decided beforehand? Yes, I could, but that would take the excitement out of it. So we have to. First of all, we can't separate variables because we don't even know what the function is on the right-hand side. So that's a problem. But we can find the integrating factor, yeah? So here we go, I exponential of, and I guess you could do this integral before you write this down, But I'm going to do it like this. And what's the integral of 3 over x squared? I think I've got a minus 3 over x, yeah?
Yeah.
All right. Oh, yeah, I guess this is a e to the minus 3 over x then. There you go. I just made this problem so that the next step is possible for us, I think. We'll find out. So join me in the adventure. So to multiply this by that constant, multiply by the integrating factor, what do we have? We have e to the minus 3 over x dy dx plus, e to the minus 3 over x times 3 over x squared y equals to e to the minus 3 over x times the sine of, oh man, I don't think it's going to work. I don't think it's going to work. Oh, man. I wanted it to be something I can integrate. The thing that happens on the right-hand side, And I'm not sure I can integrate that. I was thinking I'm going to make a u equals e to the minus 3x substitution. But then the problem is, I'm missing a 3 over x squared. So I'll just put an x squared right about here. I think that will fix it.
So we can do this on test.
You cannot, and be thankful that you don't have to do this on test, because this is like, what I'm doing right now is like, in fact, much harder than solving problems which are given. Like this is, I mean, I'm no joking, like the hardest part about doing a PhD in some technical subject is finding questions that you can answer. That's what we're trying to do at the moment. I think this will work. So this is the reverse product rule, right? We have d dx e to the minus 3 over x y equals to, well, x squared e to the minus 3 over x times the sine of e to the minus 3 over x, which I'm really hoping we can integrate. And now we integrate both sides, right? So we have integrating. We have e to the minus 3 over x times y is equal to the integral of the sine of e to the minus 3 over x times x squared e to the minus 3 over x dx. All right. I believe, if I've done this right, we'll be able to do it with a u substitution, but I'm not overly confident at the moment. Let's try it out. U equals to e to the minus 3 over x. What's that make du? We have e to the minus 3 over x, right? Times the derivative of 3 over x, which is 3 over x squared dx. Oh, oopsie. See, yeah. What do I want to? I want to change my my problem again. This is easy though. All you need is a little red marker. We want to make this a minus 2. There we go. Minus 2. Minus 2. All right. So minus 2. With that small change, this is du. Almost, right? What am I missing? 3, right? So it's du over 3. And this is sine of u. So we can integrate. We get minus 1/3 cosine of u plus a constant. So finally, let me put this example out of its misery. Y equals to c e to the 3 over x minus 1/3 e to the 3 over x times the cosine of e to the minus 3 divided by x plus a constant. Wasn't my goal to teach you how to make problems and integration by parts today, but I guess I've done that. So let me not continue making up more examples. There's not a lot of examples in your notes. If you want more examples, I have more that I can share with you, but that's kind of all I've got for here. Yep.
Where did the second constant?
The what?
Second constant they added.
Oh, golly. Oh, sorry. No. Goodness gracious. I don't know where that came from. So sorry. All right, so listen, I'll try to bring more examples for future days, but I think that's all I have for integration by parts examples. So now we're going to turn the page, go on to the next method. And the next method is not a single method, it is a creative process. All right, it's an art. This I wouldn't say is an art. This is pretty algorithmic, really. There are if you look at the textbook and you look at the problems that Stewart has in this section, which I think is 9.4, maybe 9.5, I've forgotten. Certainly in the mission, I have recommended homework problems, I think, from Stuart, right?
Yeah.
So you can see, you can tell from that. He has some problems where you don't even have to multiply by the integrating factor because it's already reverse product rulable at the start. Like the starting point of the problem is like look at it and go, oh, reverse product rule, and then go from there, you know? So there are problems like that. Like here's a ridiculous version of one of those kinds of problems. If you have something like, you know, oh, I don't know. Let's see here. E to the x squared times dy dx plus 2x e to the x squared times y is equal to, you know, tangent of x. Like he might have a problem like that. This is still in the same general vicinity of the you know, integrating factor method problem. It's just that it's brought you in at like step 4. See, because you just need to look at this and go, oh, well that's really just d dx of what? Of e to the x squared times y, right? So we have e to the x squared times y is equal to the integral of tangent x dx, right? Which is what? Natural log of the absolute value of secant of x plus a constant. So your answer is y is equal to e to the minus x squared log of the absolute value of secant plus c e to the minus x squared. So, you know, it's a lot more work to come up with problems that start you at the, the proper starting point, and then you go through it like my example 3. But he has there's about if I remember right, it's about 10 of these in Stuart. All right, moving on. How would you solve dy dx equals to x plus y minus 6 squared? We're in my section 5 right now, which is page 13 of my first order article, if you're wondering. So what do you think? How will we bend this problem to our will? How about this? Let's let v equal to x plus y minus 6. Right? If we do that, what's dv dx equal to? One plus dy dx, right? Do you agree? And then what? Well, then we can substitute that in, right? So dy dx is equal to what? Yeah, dy dx is, what did you just tell me? dv dx minus 1? Okay. And so our original problem then becomes what? It becomes dv dx minus 1 equals to, well, v squared. Which is not so bad. See, because then this gives us dv dx equals to v squared plus 1, which then we can separate, and we get dv over v squared plus 1 equals to dx, which you can integrate. What's the integral of dv over v squared plus 1? I'll start it again over here. Get rid of this mess. So we had dv over v squared plus 1 equal integral dx. And what do you tell me? Arctangent? Arctangent v is equal to x plus a constant, which is to say that v is the tangent of x plus a constant. But what was v? Oh, v was x plus y minus 6 equals to the tangent of x plus a constant. Solve for y. We've got 6 minus x plus the tangent of x plus c. There you go. Solved. So this is an example of substitution. I think sort of as a generic point of advice, substitution, what you tend to do is, pick the biggest, baddest thing looking in your differential equation and make the substitution of that, right? It's like going to prison, punching the big guy in the nose or whatever, like that, but with math. Yeah, is there a question?
So when it goes to the integral at the bottom right there,
Mm-hmm.
In my head that would be v squared plus 1 over dx. Like, how do you get to dv over v squared?
I divide both sides by the v squared plus 1, and I multiply the dx to the other side. So, yeah.
Can you just explain how dv dx equals 1 plus dy dx?
Oh, I'm differentiating this right here. So if I take the derivative of that, the derivative of x with respect to x is 1. Derivative of y with respect to x is dy dx. And then derivative of minus 6, well, 0. Mm-hmm. Okay, so, well, that went nicely, right? But you can imagine there might be another problem that after you do the substitution, what happens? Instead of getting a separation of variables problem, you get a integrating factor problem, right? These methods combine. And yeah, maybe the integral was a secant cubed. It's kind of dark. You're wishing a secant cubed upon me. I mean, that's not friendly. Let's see here. Can I, yes?
When you made v equal to x plus y minus 6, did you have to take the derivative of that to find what dv equals or anything like that?
Yes, I had to take the derivative of that to understand how dv relates to dy dx. Exactly. I mean, so in these problems, when you're making a substitution for a differential equation, right? Generically speaking, what you're gonna end up doing is you propose a substitution, right? But you're substituting it into a differential equation, which involves what? An equation and a derivative. So you have to replace both the variables and the derivatives. So yeah, usually we're going to make a substitution. We're going to have to differentiate the substitution to understand how the substituted variable interacts with the original variables. Let's do another. I think the next example will help this come to life a little bit more. Example 6. Here it is. We've got dy dx equal to y over x plus 1. Oh, this marker smells bad. Y over x. It smells like death. Golly. Ugh. Where's these notes? Hope it's not me. Let's see. Let's see here. So then, where was I? Yes. So what do you guys think?
Multiply everything by x.
Interesting, but not what I'm looking for. So what substitution would you make? I mean, that's probably what I would do, independent of this conversation, what you guys just said, multiply by x. But here, let's try to isolate the evil, give it a name. What's the evil?
Y over x.
Y over x, right. So v equals y over x. And here's a pro tip for you. Learn to hate fractions. So if you hate fractions, what you do is undo them. So this gives us x times v equals to y. which is ever so much more lovely to work with when you're calculating dv dx. See, because now to figure out dv dx, I just differentiate this. I've got, v plus x dv dx. I love the way that sounds, which is dy dx, right? Voila. Now we know how to substitute that in. So making that substitution, right? This guy is in fact these. Put that up in there. What you got? You've got v plus x dv dx equals to, apparently, v plus 1 over v minus 1. Which is kind of scary looking, but let's see if we can make it better. So this is x dv dx equals to v plus 1 over v minus 1 minus v, right? Make a common denominator. What you got? Yeah, v, what did you tell me? V plus 1 minus v times v minus 1? You're probably telling me how it simplifies. How did it go?
V squared plus 1 or plus 2.
You don't know. Let's see here. Is there anything canceling? I don't know.
There is.
There's a v that, the v cancels with the minus v. So we've really just got 1 minus v squared. Is that right? No, it's a 2v. All right, let me do it over here since I run out of space, and I haven't fixed this room yet. So, so that's a plus. I heard a plus 2v minus a v squared divided by v minus 1. I'm sorry, I may be drifting into my "It's a me Mario" voice, but. Sorry, we were talking about that over the weekend. With my son had a birthday party, and they're talking about they're excited about this new Mario movie, of course, So are you? Okay. Does that does something, doesn't it? Factor out the negative. So that's v squared minus 2v minus 1 over 1 minus v, right? That's v minus 1 squared. Hey, so that's really just minus v minus 1, right?
V minus 1 squared would be plus 1. Isn't that not worse?
Oh, is that not it? My bad. Sorry, I always do bad when I work down here. Let me continue working over here.